In this last video, we are going to discuss a popular sorting algorithm called heap sort, which uses min heaps. So the idea behind heap sort is very similar to selection sort, which we saw in the first week's videos. So the idea behind selection sort is that if we find the first smallest element, then we find out the next smallest, then the third smallest, and so on. So how this works in a heap is, what if we just extract minimum elements, which is, we know the extract min operation that is available in a min heap. What if we call this extract min again and again till our heap is empty, which is you insert n items into this heap, or insert, like, let's say if we have an array that is like 15, 27, 5, 1. This is an unsorted array. So you insert these values in a heap. Our heap would look something like this, which is 15, then we'll add 27, then we'll add 5. Now 5 violates the property of min heaps because 15 is greater than 55. So 15 will move down and 5 will go up. Next, when we insert 1, it's going to be appended right here. Now 1 is smaller, so 1 and 27 will be swapped, and then 1 and 5 will be swapped as well. So inserting like all these elements into a heap, like, which is, if we have n elements, if we try to insert them, it will take like log n time for each element to be inserted. So the total time will be n log n. Next, if we perform the remove operation, which is if we extract one element from a heap one at a time, it takes log n time to process like one operation. So if we are repeatedly doing it like n times, we are removing elements from the heap, it will take again like n log n. So it will be like n log n plus n log n, and the performance is basically being will be proportional to O of n log n. Now, what is the problem with this approach? Pause the video and think about it for a second. Like, what are the cons of this approach? The issue is, like, let's say if you have a large array, and if we try to build a heap, which is if we try to insert n items, first of all, we need separate space, which is we need again like O of n space to store like a new heap. So how we can optimize this further is, instead of creating like a new memory space, what if we can change our existing array to satisfy the heap property, which is what if we do the sorting in place itself rather than creating like a new chunk of memory. So it turns out that we can do that, which is what you can do is you can change your existing array by using just these three lines of code, which is you build the heap in place by following these two lines, which is you start your loop from size divided by 2 and you run it down. For each element, you basically heapify it down for each element. So it's going to take like O of n complexity. And why this works, like, you might not be understanding it at all, but how this works is, first of all, like, if we see this heap, we know that all the leaves already satisfy this heap property in the array, because since it doesn't have any children, we do not care anything about these children. Next, what we care about is, like, let's say if we let me just like create a new array, which is like, which we have like 15, 22, and 5, 1. Our array would look something like this: 15, 22, 5, and 1. Now what is happening here is we started the loop at the non-leaf elements. So in this case, our tree would look something like this, which is 15, 22, 5, and 1. And this does not satisfy the heap property because 1 is like the smallest element and it's not at the root. So what we are going to do is, we know, like, we'll start level by level and we'll start at the bottomest level. So the bottomest level already is satisfying the heap property because 1 is satisfying the heap property if you look at this subtree. Next, So we do not need to worry about like size divided by two elements, because like if we talk about like a complete binary tree, at every level there's going to be 2 to the power 0 elements, and at the nth level it's going to be 2 to the power l. So we completely skip the last level, which has majority of the nodes. This is the first thing you need to know. Like let's say if there were no elements, there was just one leaf element, and even if we do size divided by 2, all of these can be skipped because all of these are leaves. Next, we are going to perform heapify down on each of our nodes. So I'm going to clean this a little bit. This is a leaf, this is a leaf, so we don't care. Now we are going to apply heapify down on each of the non-leaf elements. So basically 22, we are going to compare with both its children. If it violates the property, which is one is lesser, there'll be a swap, which is we are heapifying down on all of the non-leaf nodes. So one will go down and 22, one will go up and 22 will go down. Next, it's going to apply on the other non-leaf, which is 15. So 15 will go down and one will go up. And now it's a perfectly valid heap. So we basically apply heapify down on each of the non-leaf nodes, which is we are going to apply this on each of this. So what is the benefit of all this? Now, when we apply like heapify down, we know like heapify down takes log n complexity. Also, all of the inner nodes, like we know we are applying this to size minus one, which is a size divided by two. So basically, if we do like size divided by 2 into log n, size is basically n. So our overall complexity is still n by 2 log of n, right? In the worst case. But this is a very pessimistic way of finding complexity. In the real world, it wouldn't look something like n log n. Instead, it would, I would make a claim that it would just reduce to O of n. There's some math behind it, and I'll tell you why it's going to happen in this one. So what's basically happening is whenever we are applying like heapify down on this element, because we are starting from bottom up, right? So whenever we are going to apply like heapify down, this has to care about just one child. And then when we are going to apply on this one, it's just going to care about two children. Then when we are talking about the next one, it's again going to compare like two children at that level. That's why like this entire like building the heap instead of O of n log n takes like n. So there's some math behind it, which is since the node is close to the leaf, it's going to be faster for this node, then it's going to be a little bit more slow for this one, and for the root it's going to be the slowest. So let's say if it is going to make just one comparison for this node, it might be making like two comparisons for this particular level, it might be making four comparisons to this level. And if you take out like the total time to build this heap, it will look something like this. So for the n so it will take one amount of time for the second last level, which is this is the non-leaf second last level, or the last level which doesn't have leaves. It's going to take two amount of operations for the nth by fourth level, which is this level might take two operations. For this level, they are going to be n divided by 8 nodes, because as we are moving up, the number of nodes in a particular level, it's getting less. So again, like I just want to repeat this again, which is if you have one node here, there's two nodes here, three here, and then it's up to 2 to the power, sorry, 1, 2, and then 4, and then 8. It's going to be 2 to the power k nodes at the kth level. So as we are moving up, this number is getting close to 2 to the power k, which is this. But the value of the time that it's going to take is determinant on k. So if you like realign these numbers and make this in the form of series, your series would look something like this, which is going to be n by 2. The nodes at level n by 2, or they are going to be n by 2 nodes at that level, they will take like 1 unit of time. Then at the next level they are going to be n by 4 nodes, but they are going to take 2 units of time. Then it's going to be n by 8, it's going to take 3 units of time, and so on. So this can be simplified, like if we take out n from this entire equation, it's going to look something like this, which is it is 1 divided by 2 plus 2 divided by 4 plus 3 divided by 8, and so on. So we can rewrite this in the form of I divided by 2 to the power I. And if you take the sum of this actually simplifies to 2n, which is there's proof behind it. I'm not going into the proof, but basically the gist of it is that we can insert n elements by avoiding this extra space, which is we can use this new build heap operation to make sure we can build our heap in O of n time. After that, it's going to still take like O of n log n operations to remove like n elements from the heap, but at least we have built the heap without extra space. So in some scenarios we might care truly about this extra space, and we have gotten rid of that. But at the end of the day, heap sort will execute an O of n log n time, but we can still avoid the extra space. So that's pretty much it for this video. We are going to come back on the about like heaps as well as different problems we can solve using heap in the problem solving lecture. Thank you.